our next speaker is Yoshi Ueda from JEOL that will be presenting on the behalf of John Dane that was not able to join us for the conference. Yoshi, go ahead.
Thank you very much. Introduction. So thank you very much, organization, to give us some opportunity to introduce our new system. And I'm just a little bit nervous now because originally my colleague in USA, John Dane, will make some presentation. But I'm not sure why he couldn't come here due to some travel accident. But I'm not sure it's okay. Anyway, so I heard from my colleague in Netherlands yesterday. So I tried to make some presentation last night. So I'm a little nervous, but I'm doing my best from now. Okay, I will introduce What's this one? Okay. I want to talk about the three items. First of all, I'd like to introduce our new brand new GCxGC systems, and also I tried to talk about some application data combined with the GCxGC technology with our high-resolution time-of-flight system together with the pyrolysis systems. So there are three items here. So this is our history of the GCxGC systems. Since 2004, we introduced the first generation of our GCxGC system together with the high resolution. Then we have several generations until now. Then 2 years ago, we introduced a brand new GCxGC system named Active GC Alpha, so which has a very high resolution capability compared with our original. So there are three items for the new features. One is for the high resolution. We could achieve the high resolution up to the 30,000 resolution. So we installed a very long flight path for something like this. Then we could achieve 30,000 resolution. And also we implement the double stage reflector mechanism. Then it allows us to achieve the high accuracy capability. Then we can measure the high resolution capability together with the GC measurement or GC measurement. This is some data. So bottom one is the same data measured by our first generation GC systems. It has a 5,000 resolution. It is very hard to separate some hydrocarbon, which has almost same molecular weight. But in case of our new brand new system, we can separate each hydrocarbon due to the very high mass resolution, 30,000, something like this. And also we have the very high accuracy. This is one sample to measure some exact mass value by using the EI ionizers. So in this one, methyl stearate. So each fragment can be observed within the very nice, precise accuracy within the 0.1 millidalton. So we can reach the very high accuracy, not only the molecular weight ions, but also the fragment ions. So it is very easy to identify the compound by using this capability. And we are now emphasizing some importance of the soft ionization technique, because in the case of the GC measurement, EI ionization is very familiar, but in case of the EI, it is not easy to get the molecular weight information. So in that case, in the past, CI is very familiar to get the molecular ion. But recently, almost customer, the user doesn't want to use a chemical gas into your laboratory. Therefore, we introduce some FI capability or PI capability to get some molecular weight information. Our system has such kind of variety of the ion source, EI, CI also, and PI and FI. FI means a field ionization. So PI and FI is a very soft ionization technique. Therefore, it is easy to get the molecular weight information by using this technology. We developed some combination ion source, EI, FI, and FD, or EI, PI. So if you're using this combination ion source, you don't need to stop the vacuum to switch the ionization mode. You can change some mode by using some probe between the measurement. So this is a typical mass spectrum by using the Fi and Pi. 3 compounds were measured by these 2 techniques. First one is some kind of aromatic compound. Those are easy to get some molecular ion spectrum. Then in case of the Pi, the Pi has some selectivity for the such kind of aromatic compounds. So sensitivity is also very nice. But on the other hand, so for example, the normal hydrocarbon, so Pi has some little bit of fragment ion, something like this. But in case of the Fi, so we have a very clear molecular ions peak, something like this. And also the fatty acid methyl ester is also can be detected as a molecular ions, something like this. So both EI and PI technologies are very useful to get some molecular information. So from now on, I'd like to introduce some application data by using the GC together with our high resolution capability performance system together with the software ionization and together with the pyrolysis analysis. This is very complicated system. But so normally, pyrolysis analysis is used for the plastic analysis or polymer analysis. So pyrolysis is some decomposition mechanism or technique for such kind of polymer or plastics. So there are 2 modes for the pyrolysis analysis. One is the conventional pyrolysis analysis together with the GC. And another one is the EGA, evolving gas analysis measurement. In case of the normal conventional pyrolysis analysis, so sample in the pyrolyzer heated up very quickly. Then every decomposition compound introduced into the capillary column at the same time. Then capillary column separate such kind of decomposition mixture by using the chromatographic technology. This is a very, let's say, straightforward technique for the pyrolysis analysis. Then another one is the EGA mass spectrometer. In that case, we don't use any capillary column. We just use a capillary tube without any liquid phase. Then we keep the very high temperature for the GC. Then we apply the very programmed temperature on the pyrolyzer furnace. It means that we could get some temperature profile of the samples. So it means that it is easy to understand what kind of chemicals will be generated at a certain temperature, something like this. But the problem of the EGA analysis is that there's no separation technology. Therefore, it is hard to get some mixture information from the EGA. So I try to combine with the GC by GC technology for the conventional PY-GC-MS and also EGA-MS. So first of all, I'd like to start conventional PY-GC-MS technology. So as I mentioned before, conventional pyrolysis analysis creates a huge amount of decomposed compound from the polymer or plastic. So it is very hard to separate everything by using the conventional 1D chromatographic technology. Therefore, we applied GC by GC technology onto this pyrolysis analysis. In this case, we are using some nitrile rubber as a test sample. Then we apply this nitrile rubber onto the pyrolyzer system, then together with the GC by GC technology, together with our GC time system. This is a 2-dimensional chromatogram, which was observed from the nitrile rubber. Left-hand side is a chromatogram from the EI ionization. So there are many compounds there. Then if you can see that clearly, so we can separate clearly 4 kinds of the additives from the rubber samples. Then in the case of the right-hand side chromatogram, this is coming from the Fi ionization. It's much simpler than the EI, but we can also clearly identify the 4 kinds of the additives from this chromatogram. So these are some mass spectrum of the EI and the FI by using the such kind of GC technology separation. So upper 2, we can get some molecular weight information even in the EI mass spectrum, but the lower 2 doesn't have any information about the molecular weight. So of course we can use a library search to identify these compounds by using the EI mass spectrum, but it is very difficult to identify just only one compound because there are many compound lists will produced by the library search, which has also the high matching factor. So we need to select one of them by manual. But if once you have some molecular weight information and also the exact mass value of each peaks, we can estimate the elemental composition from the exact mass value. So it means that this candidate can be narrowed down to the 1 or several by using this kind of elemental composition information or high resolution information. So therefore, it is very important to have some molecular weight information, not only from the EI, but also the FI combination, or FI or PI, or such kind of soft ionization capability. So actually, we found some localization of such kind of additives on the lava samples, but I don't, today I will not mention about the detail here. So I will skip this slide. Then this is a summary of the conventional PY-GC by GC measurement. So in case of the pyrolysis analysis, there are many complex samples, but the GC by GC technology can be separate those complex mixture. Then we can identify or separate 4 kinds of additives from these such kind of samples. Then after that, we can identify these 4 additives by using the EI mass spectra and FI mass spectra together with a high resolution capability, something like this. Next one is the EZA mass analysis. As I mentioned before, in case of the EZA mass analysis, we don't use any capillary current. We just use a capillary tube without any liquid phase. But in such case, we don't have any separation capability for each piece. Actually, we have such kind of profile, temperature profile, but it is not clear. This part is a single compound coming from a single compound or some mixture, because we don't have any separation technology. So we decided to apply the GC by GC technology onto this EZA analysis. So this one is not 2-dimensional chromatogram, but a 2-dimensional measurement or something like this. So we located the modulator between the capillary tube and capillary current. Then we try to make some chromatographic separation just after the temperature profile, something like this. Normally, we have just the temperature profile such as the upper side, but the lower side, we can measure we can measure the mass second chromatographic separation for each slice of the temperature profile. This is some not 2-dimensional chromatogram, but this is some EZA by GC 2-dimensional profile. So as you can see here, we have the very narrower, very wider peak there. In that case, we have the two kind of the compound there. So we can clearly separate by using modulation technology together with the EZA mechanism, with the EGA measurement, something like this. Okay, let's summarize my presentation first. So we applying some GC technology onto the conventional pyrolysis analysis and also the EGA analysis. Then together with our high resolution capability and photoionization capability. So such kind of two high technology separations mechanisms and high resolution capability can identify the unknown compound from a very complex mixture, such as some pyrolysis analysis. So, but actually, we have another topics, but I didn't talk about the software. So recently, we are developing some quite unique software by using the artificial intelligence (AI). So actually, in case of the unknown compound identification, it is very hard to use a library search because as far as you don't have a standard compound, you don't have a library database. But we created the AI database from the from the structure. So this AI can create the EI mass fragment spectra from the structure. So now we have the mass spectrum data library, more than 10 million compounds. Then we can apply this database onto the unknown compound identification. I didn't mention detail about this one in this presentation, but I will. We have a booth on the poster session area. So if you have some interesting, please contact us. So this is my summary. So thank you very much for your attention. And let's go to the question or discussion.